There are two main physical characteristics that make a successful pole vaulter: height and muscle development. Dr. Peter McGinnis of the State University of New York explains that, in general, elite pole vaulters are tall, often at least 6 feet or approximately 183 centimeters tall. Taller vaulters have a natural advantage because of their long reach, which allows them to plant or strike the pole at a greater angle than their shorter counterparts. A primary goal in vaulting is to plant the pole nearly perpendicular with the runway. The greater angle between the pole and the runway ensures that the vaulter can retain the most kinetic energy possible, while reducing forward momentum so that the majority of their motion is upward, not forward. A paper published in the Journal of Electromyography and Kinesiology further found that as a result of the activation of 4 different muscle groups, the vaulters were able to achieve a 22% gain in mechanical or total energy on average. The increase was attributed to the athletes having extremely developed latissimus dorsi muscles, otherwise known as lats. The larger, more developed muscles allowed for greater muscle activation, the process by which chemical energy is converted into kinetic energy. This translates to greater speed on the runway, which allows the vaulter to rise off the plant as high as possible. Pole vaulting is a compromise between muscle and height. The ability to build muscle on a taller frame becomes more difficult. However, a shorter, stockier vaulter won't be able to maximize their planting angle. The vaulter in the video clip is Olympic medalist Shaughnessy Barber, who stands at 188 centimeters and weighs 82 kilograms. He isn't built as stocky as a weightlifter, yet isn't nearly as skinny as a long-distance runner. Finding the balance between muscle and height is key.
The most important piece of equipment is the pole. Fun fact, the poles were first made out of bamboo. Today, the poles are made of fiberglass or carbon fiber for a more lightweight pole. The poles are manufactured with ratings corresponding to the vaulter's weight. Pole stiffness and length are incredibly important for performance. Stiffness is determined when the manufacturer places a standardized amount of stress on the pole and measures how much the center of the pole is displaced. The more the pole bends, the greater the stored elastic potential energy. The EPE is essential for converting the kinetic energy associated with running into a vertical and upward movement. There are left and right grips on the pole that are typically shoulder width apart, which varies per athlete. The more experienced you are, the longer your pole becomes. This is because pole length is also determined by how high you can vault. A vault box is where the athlete plants the pole at the end of the approach. They are generally made of steel or aluminum and are placed in the ground. The crossbar is the horizontal bar that athletes must clear without knocking it over. Uprights are the vertical posts that support the crossbar. The uprights are adjustable in height. More experienced and elite pole vaulters will have their uprights on a higher setting. Fun fact, the original landing area was a heap of sawdust or sand for athletes to land on their feet. Now, improved technology and rules require mats that are essentially huge bags of foam. The mats are important for reducing the effect of the landing on the vaulter's body. Force is equal to the change in momentum over the change in time. With the constant change in momentum, as the foam on the mat compresses and the time of impact increases, the result is a reduction in the force of the mat on the athlete.
There are 3 things a pole vaulter must maximize in order to achieve the highest vault possible: the angle between pole and runway, their velocity, and the transfer of energy to the pole. In pole vaulting, it's important to maximize the angle theta, since a larger angle means that the pole will have to rotate less to become vertical. In order to maximize this angle, pole vaulters need to have an upright posture during the plant, while at the same time extend their top hand on the pole vertically. The velocity of the pole vaulter is important because of the equation 1/2 mv squared equals mg delta h. In this equation, m is the mass of the pole vaulter, which can be cancelled out. G is the gravitational constant, 9.8 meters over second squared. V is the velocity of the sprinter, and delta h is the change in the height of the pole vaulter's center of mass. So for example, if a pole vaulter plants with a velocity of 5 meters per second, his center of mass would change by 1.3 meters. If his center of mass started at 1 meter high, his jump height would be around 2.3 meters.